So we're going to go over probability distribution. A couple things we're going to have to define when we look through this graph here is our mean, and our mean value is going to fall right in the middle of our probability distribution. So I haven't drawn this perfectly, but we're going to say that this is the middle of this curve, okay? I know it's not quite perfect. The middle of the curve is essentially our mean. With our mean, we talk about how far away something is. So there's many different ways to look at it. First of all, this is actual an area. Everything under here represents 100% of the probability of an event occurring or something happening. Okay, so essentially this is 100% of the data, the entire curve. So what we'll say is the entire curve equals 100% of the probability. Okay, which also means anything to the right of the mean represents 50%, and same with to the left of it, 50%. There's essentially a mirror image to the middle. It's a symmetrical object. Now, standard deviations have to do with a number occurring under a certain deviation. So your first deviation, so we have our mean score, okay? This is our average or mean. Now, one standard deviation would be, this is our symbol represents standard deviation. So let's say that one standard deviation is here, okay? So this is the symbol we use. So that's one standard deviation plus, so above the mean. And this would be one standard deviation below the mean, okay? So what they're saying here is that in terms of probability, now these are supposed to be dead equal, so I'm going to try to fix the curve just so you get a better idea. Those are supposed to be exactly, those are supposed to be equal, so this should go like this. That's probably better. Okay, so what this first off is saying is we'll represent it with, let's say, blue. Okay, 68% of all probability falls between positive or negative one deviation for the mean. So in other words, we're just going to use a random example. Let's say our mean is the number 50, okay? And for some reason, a standard deviation for this same example will be 3, okay? So if our mean is the number 50, so say this is, let's think of a good example, drawing numbers from a hat, okay? They seem to put, the average of the numbers in the hat is 50. Maybe it's like a bingo style or something like that. One standard deviation would give you numbers up to 53 and below 47. So what they're saying is 68, I believe it's 60, yeah, 68.26. Usually they just say 68% of the information in this hat, or the numbers we're pulling out, will be between the numbers 47 and 53. Okay, so everything's going to be like that. Now, you can get farther away from that. Farther away from that, we're looking at 2 standard deviations from the mean. Okay, so this would be negative 2 standard deviations. This would be positive 2 standard deviations. Now let's say, now within 2 standard deviations, that's essentially taking your standard deviation number, which is 3, and just multiplying it by the number 2. Okay, so we would be adding it to the mean. 3 by 2 is going to be 6. So when we add it to the mean, we now know that, I'll do this part in red, between the numbers 56, and we also subtract 6 from 50, that gives us 44. And that's technically red. This is including the blue, okay? So the green, the blue and the red, there's going to be, it should be 95% of the data. Yeah, 95% of the data falls all probability is going to fall between negative 2 standard deviations and positive 2 standard deviations from the mean. Okay, now in statistics, this is usually a pretty good measurement. Okay, like if we're averaging, maybe if you're looking at averages of a class even. So students in your class, the average is 50, right? They're going to say 68% of the students in your class are getting between 53 and 47. 95% of the students are most likely getting between 56 and 44. And then from there, there's 3 standard deviations. So here's a negative 3 standard deviations. I can't believe how nice I made this. 3 standard deviations. Here we go. I know that little arrow over here wasn't great, but we'll do the rest of them green. So this is the green, red, and blue. Okay, so this is all 3 colors together. 3 standard deviations. Do you know how far up from the mean that's going to give us? 59. Yeah, exactly. So 59, and how low will it go?
41.
Yes, great. So now what this means is, I believe it's 99. It should be 99% of all of the data is going to fall between that 3 standard deviations from the mean. Okay? And now we have our process for finding the mean and finding the deviation. So within 3, and say we're doing averages again, 99% of the people in your class are getting between 59% and 41%. That's the idea between it. Now, what also helps is these percentages are also a percent of the area underneath this curve. Okay, so let's say the area under this curve, this bell curve, let's say the area was just 1, we should be using a unit, but we'll say 1 unit, okay? If all of the area under this curve is 1 unit, then between 1 standard deviation, so from here to here, we would be multiplying our percentage by our total area, okay? So the area in blue, would be that 1 unit times the 68%, which is 0.68. Does that make sense? You always turn percentage in decimal. So the area under there is 0.68 units, okay, for the blue. The area of the red and blue, again, you would take the 1 unit, which is the total area, multiply it by the 95%, or 0.95. So the area of the red and the blue is 0.95 units. And the exact same idea works with within 3 standard deviations. So the area of the green, red, and the blue altogether is 0.99 units. So that's essentially everything. So when you're looking at statistics, if you can ensure things up to 3 standard deviations from the mean, you have essentially for sure covering almost all of data. It's very, very rare to get something outside of 3 standard deviations from the mean. So that's the idea with this curve that they've given you. Okay. So let's say we need to find out how far, in terms of deviations, a mark of 57 is from the mean. Okay. So when we look at our graph, we have a good idea it's going to fall between 2 and 3 somewhere, but they may want us to actually find out exactly how far it is. Okay, you guys have a formula that the mark, which is we're looking for our z-score, so how far away it is. We take our number, which is our x value, and we'd be subtracting the mean value divided by, is it the standard deviation? Yeah, it's a standard deviation. Okay. So, from the information we got, this is our mark of 57 is our x value. So our x value is 57. Our mean we knew was 50. And our standard deviation was 3, I believe. I just gotta go double check that. Yeah, our standard deviation was the number 3. Okay, so when we go to apply it, we're trying to find the z-score for this. So our z is equal to 57, subtract 50, which is our mean, divided by a standard deviation, which is 3. Okay, so when we go to solve that, we get 57, subtract 50 equals, and we divide by 3, 2.3333. So we are 2.3 repeated standard deviations from the mean, which makes sense when we go back to our makes sense when we go back to this graph. We knew that it was going to be 2.3. We knew it was going to be between 2 and 3 standard deviations away. So we can solve exactly that the mark of 57 will be, and we know it's plus 2.3 standard deviations from the mean. If it was a mark below the mean, then an equivalent mark below the mean would be 7 units to the left, right? Because we're using the number 50, it's pretty easy to find like a symmetrical value. So we went up 7 units from the mean. If I were to go down 7 units from the mean, that would be 43. So the mark of 43 would be negative 2.3 standard deviations from the mean. Does that idea make sense? And we'll do the exact same thing. What I'll say this time, we'll call this example 2. So same idea. Let's say we have another number. This time it'll be a mark of we'll do a large extremity, something that would be very, very rare, okay, just to see how far away it would be. This will say the number of 39, maybe. That's not 39, okay. So with the information we have, we know our formula up there. We're looking for our z-score. Z is equal to, our x will be 39, the mean was 50, and the standard deviation was the number 3. When we go to plug them in, 39 subtract 50 divided by 3. When we go to plug that in the calculator, 39 subtract 50 divide 3. 3, negative 3.6. Okay, so that's very far away. Negative 3.6. Standard deviations from the mean. That's very, very rare to get a number that low. So in terms of if we're trying to think of your class, it is very unlikely anyone has a mark as low as 39. It's most likely everything is going to fall between 41 and 59. So maybe another question reads, let's say example 3. Example 3 is reading, they want to know how many people in the class are getting marks between, let's say 50 and what was the one number we used? 57, right? 57. Okay. So we're going to look at this marks between 50 and 57. Well, we knew that 57 was from our information before positive 2.3, right? Yeah. Positive 2.33 standard deviations above the mean. So we go and check our z-score table at the back here. And what you're going to look for is your actual z. This is essentially our z. Our z was equal to positive 2.33. I think it was on. So on our z-score table, we looked this up, and they told us area between mean which was our number, which is also essentially the area between our symbol here and what we found to be positive 2.33 standard deviations. So, try to quickly make sense of that with a little graph. What they're talking about is they have their bell curve. Okay. So something like that. There's our mean. And we knew that, we'll say that this is 2.33 standard deviations above. So what they're saying is area in here, all of this area is equal to, what did we just say? Did we write it down? Oh, what did they say it was? 233 was 49.01. Okay, so we discovered to be 49.01, so essentially 49%. So what that's saying is 49% of the class is getting between 50 and 57, okay? Which makes sense. When we go back to relate it to our other numbers here, we had said that 2 standard deviations was essentially 95% of the data, right? But if we're only going from here to here, that's essentially half of 95. So if I'm talking about just this area here, so that's that part of it, you know what, we'll relate it to the other one because we have a little more room here. I'm going to blow that one up. Okay, so again with what we were saying before, let's redraw our chart quickly. Okay, so we have our chart, and we know that our mean falls right in the middle, and it was the number 50 from what we argued. Now, obviously this isn't drawn great, but our standard deviation was, let's say, plus 2.3, so it was to here. Now we know that 2 standard deviations from here and all the way back, that'd be negative 2 standard deviations. We know that this area itself, this area here, we knew was 95% of the data, right? But what that was is from this point to this point. So if I'm talking between, and our mean was the number 50, we were looking for the amount of information between 50 and 57. They told us it was 49, essentially 49%, correct? They said that this was 49% of the data. So in other words, in terms of area, it's 49%. Let's try to make sense of that. If between this and this is 95, then from here, the mean to 2 standard deviations would be what? Do you know how we'd solve that? All we have to do is find half of 95, okay? Because essentially we're taking, the mean is always the dead middle. So what we're saying is from here to here, area is 95. So that's all of this. Since we're only taking half of this, we're taking half of that 95%. So in terms of area, 95% divided by 2, we're going to end up with 47.5, right? So that's 47.5. So what they're saying there is from this all the way down to this is 47.5%. That means it probably makes sense that, because this is really a small area when we get down to it, there's probably another only 1.5% of the data. This makes sense. 49% of people in the class getting between those marks makes sense. It's almost half of the possible people in the class. If we went back the other way, we'd have a much larger number also. Okay, so relating to the exact same thing, we'll call this example 3. This will be example 4. We were talking about people between 50 and 57%. Let's talk about people above. What percentage of class is getting above 57? Okay. So there's another idea. We would still have to find the same z-score, which we had found to be 2.33. Now, if we know that 49 point, it's technically 0.1, I believe, right? That was the area underneath. Well, we're looking for above 57. So the only information we do have is I know from here all the way to the final point where it touches. Do you know how much of the data that is? In terms of a percentage or a unit? Remember I told you the...
you divide it by 2.
Yeah, so remember I told you this total curve is an area of 1 unit, okay? Or it's essentially, another way to say it, this is 100% of the data. Everything falls underneath this curve. Everything possible. Under here is 100% of the data. That'll all go away. So if I were to go from the midway point to the end, what percentage of the data would fall from there?
50.
Yeah, 50. That'd be half of the data, okay? So we also know that anything between 50 and 57 is 49.1. So we know that, again, that's going to be half the data. So we're working with 50%. And we know up to 2.33 standard deviations, or the mark of 57, people getting 50, between 50, so we're going to say 50 and 57. We know that that's 49.01, right? So that's going from the number 50 to 57. We know that that's 49.01% of the data. So how would we figure out the small percentage or the small area after? How many people are above 57 in the class? Do you have any idea what we would do?
No.
No? Okay. That's all right. Let's try to look at this while we go through it. Okay. Again.
Didn't you just do 50 minus 49.01?
Yeah, exactly. That's exactly what we have to do. Because we know that that represents half of the area, we just take the number 50, which is 50% of the data, subtract the 49.01, that's not 1, 01, which is going to give us approximately, I think, 0.99, is it? Yeah. Just double check. Perfect. 0.99. We would round that, okay? We would say approximately 1% of the people in the class have a mark above 57. 1% are above a mark of 57 in this class. So it's very rare for anyone to be doing better than 57 in this class. Terrible class. So if they hadn't just given this question and we hadn't worked on example 3, and they said what percentage of the class is getting above 57, okay, then we would actually have to find the z-score. Let's do a question similar to that. Okay, so using the exact same information we had before, what percent of students are getting between 45 and 52 in terms of their marks in this class? Okay. So right now, I have no idea what the z-scores are for 45 and 52. We do know our formula, which is our z is equal to our x, subtract the mean, divided by a standard deviation. We know that our mean is the number 50, our standard deviation is 3. Okay. I'm going to have to work with two questions here. I'm going to have to find the z-score for 45, and I'm going to have to find the z-score for 52. Okay. So first off, we'll find the z-score of 45. We'll do it in blue. Okay. So our x is 45. So our z-score is going to be 45, subtract the 50, divided by the number 3. That gives us 45 minus 50 equals divided by 3. 1.6. Sorry, negative 1.6, we'll say 7. Okay. So we have a z-score of negative 1.67, and our other part of the question said the number 52 as our x, right? So score of 52. So again, looking for our z-score, we have the number 52. We're subtracting our mean and dividing by our standard deviation, which will give us 2 over 3. 2 divided 3, 0.67. So our z was equal to positive 0.67. Now, when we go to look on our z-score table, let's look it up quickly. So when we look this up, we got area between our mean and our z-score, which is our x. The area between we found to be 0.67, which was 24.86. So 24.86%. And the same idea here, negative 1.67. 1.67 gave us 45.25. So same information, area between our mean, and this time it's to the left of the mean, right? Because we have a negative number. So our x number was to the left of the mean. We got 45.25. So 45.25%. So the question was asking us, what percentage of students are getting between 45 and 52? Make a small little chart. It's always good to draw a diagram because it helps us get a visual of what we're trying to say. Okay, we have there. We have our mean. The information was telling us that negative 1.67 standard deviations from the mean of the number 50. That was the number, when we start with 45. So that's the number 45. Our z-score table told us that this was 45.25% of people. Okay, that's from the middle to there. Our other information was to positive 0.67 standard deviations. So it's going to be a number closer, right? This, because it's less than 1 standard deviation, it's closer than negative 1.67. They said that this area is only 24.86% of the people. So what we're trying to find specifically is between 45 and the number 52. So we're looking for all of the area between 45 and 52. So in order to solve everybody in the class, what would we end up doing? Yeah, we just got to add 45.25 plus 24.86. So plus 24.86, 70.11. So in other words, 70.11% of people in the class are getting between 45 and 52. Now, one quick add-on to this. They might say part B of this question, what percent are getting below 45 and above 52? Okay, so I asked you what percent would be getting below 45 and 52. You realize that because of our bell curve, we know that from here to the end is 50% and here to the end is 50%. So you took these percentages and you decided to subtract them both from 50, which made perfect sense. We found that 4.75% of the class is below 45 and 25.14% of the class is above 52. So as a total percentage, there's almost 30% of the class is either below or above 52. Another way you could have done that is because we had the number 70. If I had actually taken, the curve is a total of 100%, so we'll call this a side calculation. We could have also done 100 subtract the 70, 11, and that would have gave us our 29.89 also. Either of those are good methods to solve that. Okay, so they also given us this formula. This is to even solve for what our actual numbers are. What they did is our first formula there, and we now have a second formula. They just actually rearranged the first formula to get that. So if you remember algebra rules, what I'll do is I'll start with the first formula. Okay, so call that our formula 1, which is our z was equal to x minus the mean divided by standard deviation. Okay, all they did is they decided to isolate for the variable x. So first they moved standard deviation. Because it's a division sign, when I move it over, it becomes a multiplication sign. Does that make sense? Okay. So we end up with z times, so we could say in brackets, times the standard deviation is equal to, so now this standard deviation is gone on this side, and we have x minus our mean. Okay. Z times the standard deviation, we don't know what it is, so we're just going to represent it as z and standard deviation. Okay. They mean multiply by each other. So we have z standard deviation is equal to x minus the mean. And now when I go to bring the mean over to the other side, because we're trying to isolate for just x, because it's a negative sign, mean becomes positive on the other side. So we get z standard deviation plus the mean is equal to our x, whatever our value is. So this was actually our second equation. All they did was rearrange the first one to get to the second. So if you ever get confused and they're asking you, maybe they give you the z-score, the standard deviation, and the mean, and they want you to find out what number they were talking about, you can always start with the formula they gave you and rearrange it if you can't remember this one. Or vice versa. Say you only remember this one and you need to solve for the z-score, you just isolate a variable. So you move it back and forth. Okay, question wants us to find top 10% with a mean of 20,000, a standard deviation of $1,500, and a z-score equal to 1.28. Okay. I can either use Formula 1 or Formula 2. Now, because they're looking for x, Formula 2 will be the easier of the two to use. It will be a little harder to rearrange Formula 1, but either of them will work. Let's plug in our second formula there, which is z times the standard deviation plus the mean is equal to our x. Okay. So our z is 128. So we plug that in for z, we get 1.28 times our standard deviation, which is 1,500, plus mean, and I'm just going to leave it as mean because I'm running out of space right now. 1.28 times 1,500, 1920. So we get 1920 plus our mean, which is 20,000. 20,000 is equal to x. So we add 20,000 to that. 21. We found out 21,920 equal x. So what they're saying here, we've got to relate it back again. Let's quickly relate this back to a small chart. Our mean was 20,000. They had a standard deviation of what? Positive 1.28. Okay. So standard deviation, we know that we'll say that this was one deviation. So this was a deviation. We'll say that's two deviations. Their number fell, I'll do it in red, at 1.28 deviations. 1.28 deviations. We were looking for the actual term. Okay. We also knew that a deviation was $1,500. So we plugged that all in. Assuming that what they're saying is they're looking for the top 10%, we're looking for a number that is above $21,920. So in other words, I'm assuming what they're saying is 1.28. When we go to look at it, what they mean is that this area here is 40% of the data. Anything between the mean and 1.28. Let's verify that by looking in the back, just so we can make sense. 1.28, 39.97. So that's essentially 40. That's exactly what they're saying. So what they're saying is between the mean, we'll do it in blue, between the mean and 1.28 is roughly 40% of the data. So because they're saying find the top 10% threshold, what they're saying is anything above this would be the top 10% threshold. Anything above that, $21,920, any money above that is the top 10% of whatever, maybe it's money makers or people getting paid, something like that. Okay, so the next chapter is kind of dealing with populations. Okay, and what they're saying here is they use the example of an IQ test. Okay, so let's pretend that this circle represents the entire world. Okay, everybody in the world's IQ falls under this. Everybody's IQ is in there. We have a mean IQ of 100 and a standard deviation of 15 units from there. So everybody in the world falls under these requirements, essentially. Now, what they're saying is, let's say they took a sample size of just a smaller part of the world. Okay, so big circle's world. Maybe we decide to interview, I know this isn't really to scale, but 10 people is what they use. So this is 10 people out of the entire world. Okay? Now what's going to happen there is that your standard deviations won't quite work the same. Okay? It'll be a little different. So they have a formula to find out the actual standard deviation of a sample size. So their formula is a standard deviation of a sample size is equal to your normal standard deviation, which is 15, divided by the root of your sample size, which is n. I'm just going to put that up on the... Okay, so we've now put the formula over there. So what they're saying here is to find the standard error, the error in your measurements. This will be the formula for standard error. Okay, so this is our standard error. To solve it, we would be plugging in the numbers we have of our mean and our standard deviation and, our sample size, which was the number 10 we found out. So to find our standard error, we take our standard deviation, which is 15, and we root our sample size, which is the number 10. Okay? So we take the number, first let's root 10. 10 square rooted gives us 1.6. So essentially we have 15 divided by 3.16, it goes on, is equal to 3.16227. So 15 divided 0.16227, 4.74. So we have a standard error of 4.74. that's how we go about calculating our standard. Okay, so what they're saying here is his standard error. Because he's only interviewing 10 people, okay, and say he wanted to find the mean from those 10 people. Well, he interviews and he finds different IQs. He finds maybe 121, 98. So let's say he finds 10 IQs. So 1, 2, 4, 5, 6, 7, 8, 9, 10. This guy finds 10 different IQs. 121, 100, 98, 80, 70, 130, 115, 110, 102, and 99. He finds them all. He goes and finds the mean to them, which I better find. So he found the mean to be 102.5. Okay. Now that's not actually the mean of normal IQ, right? Normal IQ is 100. So he didn't actually find the true mean. This standard error is saying that his mean will be roughly 4.74 units plus or minus the real mean. Okay, so we know that our real mean was the number 100. If he was to add 4.74 or he was to subtract 4.74 from those numbers, he's going to find a mean that's going to range from 104.7 going to range from 104.7 to 100 subtract 4.74, 95.26, 95.26, which is exactly what happened. He found a mean that fell in between this range. It wasn't the true mean, but it's going to fall between there because he hasn't taken a sample size of the entire world. He has a very small sample size, especially in terms of 7 billion people, right? He only took the sample of 10 people. So their standard error is telling you that whatever the real mean is, or even whatever his mean is, it's going to fall roughly that far away from the real mean. That's the idea of that. So with that same information, now remember, I didn't know the number 100. So what they were doing here is we had a standard error of 4.74, okay, from what we found. We found our mean to be 102. So really what they should be working with is the number 102, okay? So this is our mean. We know that our standard error of 4.74, okay, and subtract 4.74, that's going to give me a range for IQs. Say we're trying to find an IQ average because we didn't know what it was. We took the number 102.5 plus 4.75. We got 107.24 and 102.5. Subtract 4.74. 97. 97.76. This is our standard error, okay? So, in other words, this is our deviation from the mean. These represent one deviation. So we make our chart like usual. Right? We found our population size. We discovered our mean to be 102.5, right? 102.5. Our standard error said that one deviation from this, or one standard error movement, sorry, is also known as a deviation. So this is plus 1 standard error. This is minus 1 standard error. Okay. What they're saying is because remember when we were relating it back before, we know that this entire area is 100%, okay, or 1 unit. A deviation plus or minus from the mean. So what we're saying here is we knew that between one positive and negative standard deviation, do you remember what percentage this was?
40 something.
Well, the total actually ended up being 68%, right? So what they're saying is 68% of all data falls in there. So in our mean, what they're saying is this is now a confidence interval. Okay, so our confidence interval. Our confidence interval is essentially a deviation and our sample mean. So they have the formula, confidence interval is sample mean plus or minus our standard error, right? That's what our standard error formula was there. This is our confidence interval. We already calculated our confidence intervals. We know that they're between the numbers 107.24 and 97.76, okay? So our two confidence intervals were a top of 107.24 and 97.76. What this was saying was we are 68, because remember, this is also essentially our deviation. That's what we use for deviation. They are 68% sure that the true mean of the population falls between these numbers. Okay. Now, we know for a fact, because IQ, we know its true mean to be 100, right? We know that that's correct. That there's a 68% chance that it's going to fall between those two numbers, okay? So that's a 68% confidence interval. But say you're a business or something, usually you want a little more confidence than that. So you might do a confidence interval. Now this is a 68% confidence interval, okay? Let's say we want a 95% confidence interval. We're talking about sample mean again, plus or minus. Do you remember what deviation represented 95% of the area? Yeah. So -2 deviations, +2 deviations. So that's our sample mean plus or minus 2 standard errors, okay? Because remember, they're talking about a standard error. And our standard error was at number 4. So we would find it again. Our standard error, we knew it to be 4.74, right? So now our mean, which was our, let's find our numbers up here. This was our mean, our sample mean, and 4.74 was our standard error. We go and we take those numbers. So we take 102.5 plus 2 times 4.74, and same idea, 102.5 minus 2 times 1.74 to find a 95% confidence interval. Okay, so what's going to happen is we're going to have an even larger range. So what we'll take is 2 times 4. Actually, it's a better way to do this. We can do 102.5 plus brackets 2 times 4.74 and brackets equals 111.98, or we do 102.5 subtract brackets 2 times 4, 7 and brackets 93.02. So now here's our new range, okay, which is essentially 2 standard errors from the mean. We found the mean to be 102, or our sample mean to be 102.5. We are 95% confident that the true mean of the population falls between 111.98 and 93.02. Again, we know the true mean to be 100, so we know that it ended up working, our confidence interval. And finally, just theoretically, we're not going to quite solve it, a 99% confidence interval. Do you know what that would be? 3 times our standard error, whatever that is. So we would do the exact same idea, and we have an even larger range. So the bigger the range is in the number, let's look at both of them. So, did we do this all on one page? Oh, I guess we did. So we do that too. Oh, okay. Yeah. So the bigger the ranges of the number, the more likely we have found the true mean to be in there. And that's why we work with larger confidence intervals. We we found our mean. We only sampled 10 people out of the total population, right? The larger our sample size, the smaller our standard error is going to become. So the more people we interview, the standard error becomes smaller and smaller, and we start to really focus around the true mean of the population. Change that. So we technically need to fix those numbers there. Apologize. I thought they would just use 2 standard deviations, but they want to be very specific. For a 95% confidence interval, they want the number 1.96. 1.96 times the standard error. So same idea, 1.96, 1.96. It's going to change our numbers a little. Okay, it'll make them a little tighter. They'll be a little closer together. And then 99% confidence interval is not 3 standard deviations, but actually 2.58 of the standard error. Is that what they said, right? 2.58? Yeah, plus or minus 2.58. So, sorry, fix that part. Same idea, we would plug the numbers in, 102.5. We'll just make sure plus 1.96 times 4.74. Oh, I didn't type it in the calculator. Oh, I did. Plus. Oh, 11.7. That makes sense. Yeah, that's roughly the exact same number we found, right? And there you go, that's the other one, 93. So, pretty much the same numbers we found before. It's just a little tighter than the ones we had. Okay, on page 138 in your book, they have the step-by-step of confidence intervals using T. Okay? So what has happened is this lady has looked into kindergartners cooperating with each other. She randomly puts down, observes a group of kindergartners play for 30 and notes the number of cooperative acts engaged by each child. So one kid, he cooperated once. Another kid cooperated 5 times. Another guy twice. Another one 3. Another 4. 1 twice, 4 and 3. So there was actually 1, 2, 3. There's 10 kids in this study. Okay? So she observed 10 different kids, and she needs to first find the mean. Okay, so we need to find the mean, or the sample size mean, which is also, I think it's usually represented as bar x. Okay, so the sample mean, she adds them all together. We get 1 plus 5 plus 2 plus 3 plus 4 plus 1 plus 2 plus 2 plus 4 plus 3. 27 divided by our 10. 2.7 was our sample mean. Okay? So our sample mean is the number 2.7, which is essentially what they found here in their first step. Obtain the standard deviation. So we have to square everything. So we have all of our numbers. I'm going to just move our sample mean down to the bottom here. There was our sample mean. We know in order to find a standard deviation, we actually have to square the difference between, okay, so what we're going to find is each of these squared. That'll give us 1, 25, 4, 9, 16, 1, 4, 4, 16, and 3. Add them all up. They've actually nicely done it for us in the book. The sum of all of these is 89. And now to find the standard deviation, they have a strict formula, okay? So this formula is S is equal to the root of the sum of all the square numbers, okay, divided by the sample size, minus the mean squared. The mean squared. Okay. So remember, is our sample mean. And and we knew our sample mean to be 2.7. The sum of all squared numbers is 89, and our n in this case is 10, because we know there's 10 kids, right? So to solve this, the sum of those numbers was 89. Does that make sense? Divided by 10 as our sample size, minus 2.7 squared. And we got to find the square root of all that. So we do 89 divided by 10, 8.9. We'll do this one step at a time. Root of 8.9, subtract 2.7 squared, 7.29. 7.29 is going to equal the square root of 8.9 subtract 7.29, 1.61. So our standard deviation, we square root that number, 1.26. 1.26. So this is our standard deviation of a sample mean. Okay. Another thing they want us to find is the estimated standard error, which is this formula here. This represents our estimated standard error. This is our standard error, which we found on the previous page. Our standard error was 1.26. We had that before. Our sample size was the number 10. Okay? Which is simple. They only needed 2 variables for this. So we took 1.26 and we divided by the root of 10, because that's our sample size, subtract 1. So essentially, we're looking for 1.26 divided by the root of 9. Okay? So I take 1, oh no, I didn't write 26 there. 1.26 divided by bracket 9 square rooted and bracket equals 0.42. 0.42, does that make sense? Yeah. 423 they used. We didn't round it as well. Okay, so we've now found our standard error, which is 0.42. Then in our t-charts, when you look up a t-chart, determine the value of t from the table. So D at F, which is like the left side of the t-chart, will be your population subtract 1. Our population was 10, so our D at F will be 10 subtract 1, which is 9. So that's the number we're looking for on the left. Now, we're looking for a confidence interval of 95%. So we have to determine our level of significance. Okay, we take that 95% and we subtract from 100. Subtract from 100, we get 5%, which is known as 0.05. So on a t-chart, we're looking for 0.05. So it's like playing bingo between the numbers 9 and 0.05. On the t-chart, we discovered, when we went to look, here's 9, and level of significance, 0.05, 2.262. Does that make sense, how I found that? Okay. So we discovered that our t value is 2.262. So obtain the margin of error by multiplying the standard error by the mean, of the mean by blah. So our standard error, so we're looking right now for the margin of error. So margin of error is like our standard deviations we were solving before, or our standard error in the questions before. So they just use this to represent it. They say the standard error is our margin of error. Margin of error is our t times our s x bar. Okay. We found our sx, or our standard error, to be 0.42, and we found our t value to be 2.26, right? So s was 0.42. So our margin of error is those two numbers multiplied by each other, 2.262 times 0.42. Okay. Times 2.262 equals 0.95. They rounded it, because they had a 3 at the end. So they rounded it to 0.96. 96. Okay, so sorry, let's type their number in. 0.423 times 2.262. Yeah, that rounds to 96. So they round a margin error of 0.96. So in other words, what they're saying now is to find the confidence interval, so a 95% confidence interval is going to be equal to our sample mean, which we found way earlier, plus or minus our margin of error, and our margin error is this number. They represent margin of error by saying T S X bar. That's the symbol they use for margin of error. So we add, subtract T times our standard error. Okay. So our mean, which we found way earlier, was 2.7, correct? We found that the average cooperation act, or the amount of times a kindergarten would cooperate on average, was 2.7 times. And we know there's going to be a margin of error of plus 0.96 and subtract 0.96. Now this is no longer standard deviation. This is finding exactly a 95% confidence interval, okay? Because we've already calculated our margin of error. So we know with 95% confidence, 2.7 plus 0.96, 3.66, 0.66, and 2.7 subtract 0.96, 1.74. 1.74. Okay. So we know with 95% confidence that kindergartens will cooperate. The average cooperation rate for kindergartners is somewhere between 3.66 and 1.74. Another type of question is when we're dealing with proportions. So remember, we were dealing with means and averages before. Now we're dealing with percentages of people. So the question here says that 45% of college students, and there's 100 people interviewed, so N was 100. 45% said they wanted to legalize drugs, or they think it was good. So 45% said yes to that question, which means what percentage said no? Yeah, 55% said no. Okay. What they're saying now is this is called a standard error of the proportions, which we've been calculating as margin of error before, or standard error. Those are all different types of things. They're talking about the standard error of the proportion. So this is S at P. They just have a different way of calculating it. S at P is the proportion who agreed, which is that, multiplied by P subtract 1, which is essentially the proportion who don't agree, right? Proportion of 45. If we take 45, I wrote that backwards. It's 1 subtracted, not P subtracted, right? Is that what it says in the book?
Yeah.
Yeah, 1 subtracted. We took 1 and we subtract the 45%, we got 55%. So we multiply these two numbers together. 45% said yes, 55% said no, over N, which is our population size. So we need to find the square root. 45% said we should legalize it of the college students. 55 said no, they shouldn't. 100 people were interviewed. We get 0.45 times 0.55 divided by 100, and then we square root that number. 0.049. 0.049. Did they round it? Yeah. They decided to round this. 0.05. Okay. So in other words, this is our standard error. Now, if you remember with our confidence intervals, confidence interval of 68%, confidence interval was, in this one, this is going to be the proportion. They usually use mean plus or minus standard error. This is standard error proportion. 95% confidence interval is the proportion plus or minus 1.96 times standard error. And 99% confidence interval is our proportion, which is 45, plus or minus 2.58 of the standard error. Did those three things seem familiar to you? Those are the same types of numbers we used before. So let's say, once again, like in statistics, we usually aim for 95. We think that's relatively accurate. 95% confidence interval is equal to, our P was our proportion, remember that from up here, which was 45. So 45 plus or minus 1.96 times, here's our standard error, 0.05. And same idea, sorry, we'll just do the top one as plus because we want to find the range. Plus and minus 45 minus 1.96 times 0.05. So these are going to give us our range. I'm just going to move these over. Okay. So in other words, 45 plus 1.96 times 0.05 equals 45 45.098, and the other option is number 45 subtract brackets 1.96 times 0.05 and bracket equals 44.9. 44.902. Is that right? Oh, sorry. What we should have done, my mistake. It's been a long. Because these are percentages, we actually put them as decimals. Okay? So that's my error. That's why these numbers were such minuscule changes. They should have been a little bigger. They should be represented as percentages. So again, same idea, 0.45 plus 1.96 times 0.05. There we go, 0.54. Right? Is that what they get? Yeah. So 0.548. And the other option is 0.45 minus bracket 1.96 times 0.05 and bracket 0.35. 0.352. So we would turn those back into percentages. We were 95% true probability is neither smaller than 0.53 nor larger than that. So in other words, what they're saying is they're 95% sure that the true average or the true amount of students who think, or college students who think drugs should be legalized is between the numbers 35% of all of them and 55. You would round that, I guess, 55%. So the true mean, so 95% sure that the true percentage, the true percentage is between 35 and 55%. So from our sample, that's what we discovered.